If you've ever looked closely at an airplane from the airport window, you've probably noticed something strange at the very back of the aircraft, a small circular opening inside the tail section. At first glance, it almost looks like a flaw in the design, like something is missing. But it's not a mistake and not a hole in the fuselage. It's actually part of one of the most important systems in every modern airplane. Before we continue, remember subscribe, because aviation is full of details most passengers never notice, and this one is far more important than it looks. Let's keep going. That opening leads to the APU, the Auxiliary Power Unit. It may look small, but without it, a modern airplane can barely operate normally. The APU is basically a small, independent engine hidden inside the tail, and despite its size, it performs several critical functions. It has its own fuel supply using the same jet fuel as the main engines. That means it can work completely independently, even when the main engines are shut down. One of its main jobs is producing electricity while the airplane is on the ground. When passengers are boarding or leaving the aircraft, the main engines are usually turned off. But the lights, air conditioning, electronics, and onboard systems still need power. That's exactly what the APU provides. And despite generating serious power, the system is designed to stay surprisingly quiet. Most passengers barely even notice it working, even though it's actively powering the entire aircraft. The APU is placed in the tail for a reason. It's one of the safest and most efficient locations on the aircraft. The tail section is separated from the passenger cabin and cargo compartments, which reduces risk in case of fire or failure. Its exhaust gases also exit directly backward, away from the wings and main engines. But there's another important reason: balance. Positioning the APU in the tail helps distribute weight correctly without hurting aerodynamics or shifting the aircraft's center of gravity. And the APU isn't only useful on the ground. In flight, it can become a critical backup system. If both main engines fail, the APU can still provide electrical power for navigation, communication, and key flight systems. That allows pilots to keep control of the aircraft and safely continue the flight. Most passengers never think about it, but this small engine in the tail can become one of the most important systems on the entire airplane. One of the most famous examples happened on August 24, 2001. Air Transat Flight 236, an Airbus A330 flying from Toronto to Lisbon, suffered a major fuel leak over the Atlantic Ocean. Eventually, both engines failed completely. The aircraft lost all thrust and became a giant glider in the sky. The pilots had to guide the airplane toward the nearest runway, an airbase on the Azores Islands. What followed became one of the longest glide flights ever performed by a commercial airliner. And here's the incredible part. The airplane had drifted around 100 kilometers south of its original route earlier in the flight. If that hadn't happened, the aircraft likely would not have reached land at all. Systems like the APU and RAT helped keep critical instruments and flight controls working, allowing the crew to safely land the aircraft and save everyone on board. But the APU does more than just provide electricity. It also supplies compressed air used to start the main engines. And unlike a car engine, a jet engine cannot simply turn on instantly. It needs a powerful airflow to begin rotating internally. That's exactly what the APU provides. And this becomes especially important during emergencies. One famous example happened in 1989, when KLM Flight 867, a Boeing 747 flying near Alaska, accidentally entered a volcanic ash cloud. The ash caused all four engines to shut down in flight. For several terrifying minutes, the aircraft became a powerless glider. The crew repeatedly attempted to restart the engines. Eventually, they succeeded and safely landed the airplane. Systems like the APU played a critical role in keeping essential aircraft systems alive during the emergency. And in extremely cold climates, the APU also helps warm aircraft systems before departure, protecting them from freezing and possible failures. Despite its compact size, the APU isn't used only on commercial airliners. It's also widely used in military aviation, cargo aircraft, and private jets. That shows how important and universal this system really is. In military operations, the APU allows aircraft to remain fully autonomous, especially at remote airfields without ground support equipment. Cargo airlines also rely heavily on it because many freight aircraft operate in airports with very limited infrastructure. No matter how remote the location is, the APU allows the aircraft to support itself independently. And despite being relatively small, the system is built for extreme reliability. Before entering service, APUs go through severe testing, including extreme temperatures, vibrations, and heavy operational loads. Because in aviation, even the smallest systems must be ready for the worst conditions imaginable. Despite its reliability, the APU also has limits. Most systems are designed to operate at altitudes up to around 12,000 meters. Above that, the air becomes too thin, making it difficult for the APU to start properly. Different aircraft use different types of APUs. Most modern airplanes rely on small gas turbine units running on the same jet fuel as the main engines. Large aircraft like the Airbus A380 use especially powerful APUs to support massive electrical and climate control systems. Military aircraft and private jets often use different, more specialized designs. Modern APUs are also connected to digital monitoring systems that send real-time data to ground engineers. This allows problems to be detected early, improving safety and reducing maintenance delays. And here's something interesting. That loud humming sound you often hear while boarding an airplane usually comes from the APU. After takeoff, once the main engines fully power the aircraft, the APU is normally turned off to save fuel. So that small opening in the tail is far more important than it looks. It hides one of the systems that helps keep modern aviation safe, efficient, and reliable. If you enjoy discovering the hidden systems that keep airplanes flying, subscribe. Because modern aviation is far more complex than most people realize, and we'll keep breaking down the engineering behind it in the next videos.